I don't know. I'm going to have to think about that. I kind of like the way it's working out. Are we recording here? Because it didn't. Oh, I had the sound turned off. No wonder it didn't bleep. Double check that it's recording properly. It is. Okay. So 4 part 6, inverse trig functions. So this is not reciprocals. Yesterday we did reciprocals. This is inverse trig functions. So we're mapping ratios back to the angle that they originated from with respect to the triangle. So trig functions map an angle to a ratio. Inverse trig functions reverse that process from the ratio back to the angle. So the first one we'll discuss is the sine inverse. And so if we were to plot this, do you see how I'm just reversing the x and the y's here from our original? Like so. So this was the x-axis before, negative 2 pi to 2 pi. And this was the y-axis, negative 1 to 1. So I'm just using the opposite. And that's because we're mapping ratios back to angles in radians. So if we just put some points on there that we know to be true, remember that the sine of 0 is 0. So we use the ratio as the x and the angle as the y. It doesn't matter in this case because they're the same. But the origin here. And then the sine, we'll do the quadrantals. Well, let's do the halves. So the sine of pi over 2 is 1. So remember that this is the y, and this is the x in this case. So where x is 1, y is pi over 2, right there. Sine of pi is 0. Sine of 3 pi over 2 is negative 1. So you see how this is working? I'm just taking the ratios and making that the x, the angle that corresponds, making that the y. If I go to negative pi over 2, that's negative 1. Negative pi is 0. Negative 3 pi over 2 is positive 1. And negative 2 pi is 0. So we're going to connect these with a smooth curve. And that's going to be the inverse sine. But let me ask you a question. Does that pass the vertical line test? Is it a function? No, not a function. So we got to do something to make it a function. So what we do is we're going to arbitrarily constrain the range. In other words, we're just going to say certain parts of the range are valid and nothing else is. So when you think about it, mapping a ratio back to an angle, that ratio comes from an infinite number of angles, doesn't it? Because if I were to go on down through here, this spiral would continue forever. So it makes sense for us to pick the most common angles and just use those. So what we do is we say positive 90 degrees and negative 90 degrees are the only things that count. In other words, from negative pi over 2 to pi over 2. So we only consider the valid range be negative pi over 2 to pi over 2. That's it. And the domain, of course, has to be from negative 1 to 1, including both bounds. So the range and domain are pretty tightly constrained. And that's actually advantageous to us because if we plug anything outside of that domain into an inverse trig function, it throws an error. And a lot of times that's a good control for mistakes, as I said. So if you made an algebraic error and you try to plug it into a trig inverse function, it's going to say that doesn't work. So a lot of times I've caught an error on myself in that fashion. So if we graph this on the calculator, we will only see this bit because the rest of it is disconsidered. So this is the only valid bit. Now, just do a highlighter here. It's going to snap to a straight line, but you guys know that's not exactly straight. It's just slightly curved. Okay, so we'll do the sine inverse of X. And the window needs to go from negative 1.5 to 1.5 for the X. For the Y, let's go negative pi to pi. And you see, you only get the part that I highlighted. The rest of it just doesn't count. Now, that is a constraint that causes us some issues, maybe, because when we plug in a ratio into the inverse sine, it can only give us a value between negative 90 and positive 90. We're trying to find an angle in Q2. We've got to use symmetry to figure that out. It won't give us an angle in quadrant 2. It can't. Beyond the capabilities of the sine inverse. But I'll show you how that works. We'll have a couple of those here. Now let's talk about the cosine inverse. Works similarly. Once again, we turn our X into our Y, Y into our X. So let's think about some quadrantal angles here. So cosine of 0 is 1. So this is the X and this is the Y in this case, because we're inverting those. It's a functional inverse. So here we have a point. And then cosine of pi over 2 is 0. So if I go to 0, I go up to pi over 2. Cosine of pi is negative 1. So if I go to negative 1, come up to pi. And you know how it goes from there. Didn't have that point very symmetric. If I were to graph this, you see how that's not a function. So once again, we fail the vertical line test. We can't use the same constraints of it, because if I go from negative 90 to 90, you see how it still fails? So we shift our constraint of the range to go from 0 to pi. So in order to make it functional, we artificially constrain the range to go from 0 to pi. And the domain is going to be from negative 1 to 1 again. So this artificial constraint of the domain is what makes it functional. So once again, if I were to graph it, you're just going to see this part, this from 0 to pi. So if I change this to cosine inverse and I graph, you're seeing only this part. And this only goes from negative pi to pi. That's why it's reaching the top. I suppose I should make it the same. That way it's more clear what's going on. So yeah, just this bit is the part that counts. Everything else is disconsidered.
Always the case.
Yes.
Is the range always 0?
Yes, by agreement. No, this part is just as valid as this part. But the reason why we choose this, Colby, is in general, you're more likely to use an angle between 0 and 180 than you are any other angle. Just the more commonly used values. Now notice the cosine inverse can give you something in Q2. But it can't give you a negative angle. It can't give you something in Q3, et cetera, et cetera, et cetera. But it can give you an angle in quadrant 2. So it's handy for that. Tangent inverse. Let's do it. Remember that we only worried about pi to negative pi with the tangent because its period was a pi. So do that. And then remember the range for pi or for tangent was all real numbers. So in this case, the domain is going to be all real numbers. We can pick any domain value we like for the tangent. The range values will have some issues that we'll discuss. So remember how we had vertical asymptotes at pi over 2 plus n pi. So those are going to manifest as horizontal asymptotes in the inverse tangent. And remember how the tangent was always increasing. So the same will be true here. You'll have this funky shape. Do that one for me. So once again, failing the vertical line test in this case because of these values above and below. So what we're going to do is artificially constrain the domain yet again. We're going to say the range is going to be from negative pi over 2 to pi over 2. Between those first two horizontal asymptotes if you go outward from the origin. So only this part counts. And I can demonstrate that on a calculator. So I need a little bit more x, because this one again has no domain constraint, and we'll go from negative pi to pi. Same level. Negative pi. And that's the cosine, so we want the tangent this time. That's the only part that counts, the part I highlighted. The rest of it is not part of the tangent inverse. Just because we say so. There's no mathematical reason for it not to be. But the reason we chose that part is because we're more likely to use an angle in Q4 and Q1 than we are in Q2 and Q3. So this is just for convenience. Okay, so those are all the trig inverse functions. Questions about those? All right, let's get through these examples. Arcsine, cosine, arccos, and arctan is just another way to say these inverses. So this was the old way, and to be honest, the better way to describe trig inverse functions. The reason why I don't like this is because it makes you think it's to the -1 power. So the TI calculators put this on because this is more text, right? So this is a little bit more expensive to print on a button, maybe harder to fit on a button, I don't know. So the TI calcs changed it to this, and suddenly this became the standard. But traditionally, this is the way we describe a trig inverse function. So if you see arcsine, arccos, arctan, it means this. Find the exact value of sine inverse of radical 2 over 2. So we're just going to use the unit circle here. So we're worried about y values only. So we've got the first quadrant of the unit circle. The sine inverse is also defined down here, but it would have to be a negative to wind us up there. So positive, we know we're in quadrant 1. Do you see how the y value is square root of 2 over 2 right here? And so we're concerned about what angle, what base angle is represented by this ray. And that would be 45 degrees, or pi over 4. So the answer is pi over 4. We could also say 45 degrees. So good life tip, when we use a calculator to find inverses, you need to be in degree mode. Because radians as a decimal are not going to make a whole lot of sense to you. Pi over 4 is not going to be represented this way. It'll be 3.14 divided by 4, and then out to an infinite number of decimals or whatever. So degree mode when you use a functional inverse, radians when you graph. You'll be switching back and forth constantly. So we'll go to degree mode right now. Boom, baby. And then sine inverse of the square root of 2 divided by 2. And it tells us, of course, 45 degrees. All right, questions about that? So they use the same technique. Arc sine of negative radical 3 over 2. Use the same process to find it by hand. But who am I kidding? You guys are going to pull a calculator out instantly, aren't you? Not negative. So we're negative this time, and I know the y is only negative in Q4 as far as the quadrants that this arc sine is defined in. Let's see. All right, so here we go. I see negative radical 3 over 2 for the y is here. So that's that one, and that's negative pi over 3. For negative 60 degrees. So sine inverse, we're still in degree mode, so we're good. Negative square root of 3 divided by 2, negative 60 degrees. Questions about that? Okay, cool. Kind of where we're putting together a lot of ideas. Remember, we learned the unit circle, we learned about radians, we learned about degrees. All that was early in the chapter. All of it's coming together. So sine inverse of negative 2 pi. You're going to see one like this possibly on a quiz or a test, depending on which version I choose to use. Remember, the domain of the trig inverse functions is from negative 1 to 1. Is negative 2 pi between negative 1 and 1? No, this is going to throw a domain error. This has no solution. And your calculator will tell you that. But sometimes it can still be confusing unless you understand why. Because the domain of all trig inverse functions, sine and cosine, is negative 1 to 1, and then the tangent is 1 without a constraint on its domain. I can plug any dang thing into the tangent inverse. But as far as the sine inverse and cosine inverse are concerned, must be between negative 1 and 1. Sine inverse of 0, that would be 0. Did you remember the origin? So 0 radians maps to 0 ratio. Therefore, for the inverse, 0 ratio maps to 0 radians, or 0 degrees. It can be confusing if you let it. Once again, your calculator can confirm this. Sine inverse of 0 is 0. Okay, so example 2. Find the exact value of cosine inverse. This time we're dealing with the x values. So this is our ratio, 1. And remember, the cosine was this part of the unit circle, from 0 to pi. So cosine's a little different. The sine value was this part of the unit circle, sine inverse. But the cosine is the upper half. And we're concerned about the x values. They're positive in Q1, so we're looking for something in Q1. So the cosine, I see, I don't have to look any further than that. The x value is 1 right here on this ray, and that, of course, represents 0 degrees or 0 radians. So 0 radians or 0 degrees. And I can double check myself here. Second cosine 1, 0. Questions about that? Cool. So arc cos means cosine inverse. Same thing. I notice I'm negative here, so we're talking about Q2. So we got 1, 2, 3. And we're looking for where it's negative radical 3 over 2. That's right here. So that's that right. So what that's going to be is 150 degrees, which is 5 pi over 6. Radians. But again, you want your calculator in degree mode for trig inverse. Okay, so I feel pretty comfortable with arc sine, arc cos. You guys cool with those? Feel like you could do what I just did? Okay, cool. We'll go to example 3 here, which is the arc tan. A little bit funkier because we can't just use a unit circle, can we? Tangent's not on the unit circle, at least not directly. It's indirect. You have to divide the sine by the cosine. So in this case, we will rely more heavily on the calculator. In other words, it'll be more abstract. Remember also the tangent is only defined in Q4 and Q1. So the right half of the unit circle. We've thrown away the rest. Because it would be non-functional. We didn't. All right, so this value, again, more calculator reliant in this case. Tangent inverse of the square root of 3 divided by 3, I'm in degree mode, is 30 degrees. And the reason why that's the case, if I were to take that 30-degree ray, which had these values on the unit circle, and if I were to take the sine divided by the cosine, which is another way to determine the tangent, I would have 1/2 divided by radical 3 over 2. If I multiply top and bottom by 2, I get this. I rationalize, I get this. So you see how that all matches up. So you would have to do it this way to do it by hand, which is quite a bit of work. So from this point forward, with the tangent, probably as long as you understand how this mechanically works, that the tangent is the sine divided by the cosine, and I can use the unit circle, even though it's a somewhat tedious exercise, better to just use the calculator in this case. With the sine and the cosine, it's actually faster to just use the unit circle. The values are on it, than even to put it in the calculator. You'll notice I was rattling those off like in 2-3 seconds because I know the unit circle. But with this one, better to use a calculator. Arctan 1. So this is going to be easy to do mentally. Get a ratio of 1, you need the numerator and denominator to be the same. Where in quadrant 1 on the unit circle, cosine and sine the same? Very good. Pi over 4, 45 degrees. It's square root of 2, comma, square root of 2 over 2, comma, square root of 2 over 2. So I can know that one without even plugging it in the calculator. But we'll do so just to make sure. Oh yeah, baby. And this also is, of course, trying to get used to working with radians. Okay, so arctan, once again, these are calculator type problems. I won't patronize you with one so simple. Negative 60 degrees. That's what you get here. You're going to get something funky one of these days, maybe on a test or a quiz. You're going to plug this in and get like negative 0.8. What's going on? If you were to use the exact same button press as I just did and you got something crazy, what does that mean? Exactly. Mackenzie got it. You're in radian. So mental note right now, if I work these problems and my button presses aren't wrong and I get a crazy result, I'm in the wrong mode. If I try to graph and my graph looks crazy, guess what? You're in the wrong mode. So this is going to happen to you. I guarantee. It's happened to everybody, including me. So mental note right now, you need to always check that mode as a first choice. Here's your book's description of the inverse trig functions. We've already discussed the graph pretty thoroughly. So if that wasn't clear to you, you can come back and look at this. Sketch graphs of inverse trigonometric functions. So if we modify these, this is really going to stretch the brain power if you can visualize this. So what this is a horizontal stretch by a factor of 2. We're just going to stretch the tangents graph out horizontally, so it'll be kind of closer to the x-axis. So if I've already got it on here, so if I change this to oh, guess what? Wrong mode. You see how crazy that graph was? So, kind of glad that happened actually. So this same graph as before, just stretched out very subtly from the horizontal direction. All right, and then sine inverse of 2x, this would be a horizontal compression. So instead of going from -1 to 1, it would go from -1/2 to 1/2. And it would constrain your domain as well. So this one would be pretty interesting. Let's see. Sine inverse of 2x. Let's see how we're squished here. If I hit trace, -0.5. You see how that's the very edge of the graph, even though it doesn't seem to be even on the graph, but it's right at the edge. Okay, so these are the ones I wanted to really get to. So arc sine of 1/2. This is an angle. So this takes, the arc sine takes a ratio and maps it back to an angle. So then we're going to take that angle and plug it into the sine function. So, and actually the sine and the arc sine just cancel each other out. Do you see why? Because they undo what the other does. So this is just going to be 1/2. And your calculator can actually do this one, although it's not generally trustworthy for these very complex problems. First of all, it's difficult to get them in the calculator properly. Second of all, you've got some mechanical constraints that are hard to get past. So don't trust your calculator implicitly with regard to these kind of problems, although I think it's going to handle this one pretty well. Yeah, so it tells us it's 1/2. And if you ever have a ratio or a decimal you want to change to a fraction, just hit math, enter, enter. It'll change that to a fully reduced fraction for you. So these cancel each other out in this case. If I use cosine inverse of the cosine of 5 pi over 2. So this is going to map something, this 5 pi over 2 to a ratio. Then we plug it back into the cosine inverse. We go right back to that original angle in radians. So once again, we cancel each other out. The problem you're going to have here is your calculator is going to give you a decimal approximation. It can handle these. Again, not 100% trustworthy. 5 pi over 2. And we're in radian mode, so we're good. Yeah, so it gives us that. What the heck? See if that's... Okay, so here's what happened here. You know the cosine inverse is only defined between 0 and pi. So it gave us the corresponding angle for this between 0 and pi. So technically this is true, but it's outside of the range of this bad boy. So we have to map this to the upper half of the unit circle. In other words, where is its corresponding angle? And so 5 pi over 2 is the whole unit circle and then back to 90. So that's equivalent to 90 degrees for pi over 2. So this cosine inverse, because of those range constraints we put on it, can't give us this value. Even though this is the right answer, this is what it's going to give us. And this is what you'll be expected to put on a quiz or a test. So don't give me an answer for the cosine inverse that's outside of its range. Okay, and then the last one for this section that I really wanted to get to, super fun. The composition of trigonometric functions. So here, these don't cancel out. You see how this is the sine function and this is the cosine inverse? So they're not going to cancel out in the way those previous problems did. What I need to do here is say this is some angle alpha, and I'm going to create a reference triangle for alpha, not to scale. I know the cosine has the ratio of 4 over 5, so the ratio of the adjacent to the hypotenuse is 4/5. So it's some angle alpha that has this for its cosine ratio. Then I'll use the Pythagorean theorem to find this side. What is this side from? Special, say again? Well, it's a special triangle, blank 4, 5. Yeah, 3. So that one I don't even need to use the Pythagorean theorem for because it's such a common Pythagorean triple. You remember some Pythagorean triples. 3, 4, 5 is definitely worth committing to memory. That's a Pythagorean triple, and we don't have to do any calculation. We just know if we see a 4 and a 5 here, this has to be a 3. If we see a 3 and a 5 here, this has to be a 4. So the 3, 4, 5 Pythagorean triple is a good little thing to memorize for that reason. Okay, so now I need the sine of alpha, and that's going to be the opposite over the hypotenuse, or just 3/5. So the reference triangle can make these otherwise very challenging problems pretty easy. Okay, so part B here. The cosine of the arc sine of 8 over 17. So they weren't as nice to us this time. This might be some Pythagorean triple, but it's not one I know. So we've got some angle alpha. I wrote Euler's numbers. So some angle alpha in a reference triangle where the sine, in other words, the ratio of the opposite to the hypotenuse is 8 to 17. So I know 8 squared plus our unknown side b, we'll call it squared, equals 17 squared. So b squared equals 17 squared minus 8 squared. And b is going to be the square root. We're only concerned about the positive. 17 squared minus 8 squared. Here's a good time to use our calculator. So it is a Pythagorean triple, but not one I had memorized. So 8, 15, 17, another Pythagorean triple. Now we want the cosine of alpha. So that's just the adjacent to the hypotenuse. Like so. And we don't have to worry about positives or negatives here because this is positive. And if we plug a positive ratio into the arc sine, we're always going to get an answer in Q1. So we know alpha's in Q1. Don't have to worry about it being negative. Questions about anything in 4, part 6? All right, cool. Let's move on to 4, part 7. I'm going to stop the video and then restart it so that I have 2 discrete videos for these. There will be an assignment for 4, part 6. It'll be brief. Oh, I do want to save my lecture notes, though. Part 6. Save. Yoink.